Hello, I am Dr. Srinivasa, working as an assistant professor of physics. In this video, I am going to explain some concept of polarization, which is a chapter for second BSc physics students. The topics covered in this video are optical activity, types of optically active substances, Fresnel's explanation of optical rotation, effect of electric field on linearly polarized light, that is Kerr effect, effect of magnetic field on polarized light, that is Faraday's effect. First of all, what is optical activity? The phenomenon or the property of rotating the plane of polarization or vibration about the direction of propagation of polarized light by certain crystals or substances is known as optical activity. The phenomenon or the property of rotating the plane of polarization or vibration about the direction of propagation of polarized light by certain crystals or substances is known as optical activity. The substances or crystals which rotate the plane of polarization or vibration are called optically active substances. Examples of optically active substances are sugar solution, turpentine, sodium chloride, tartaric acid, quartz, quinine sulfate solution, cinnabar, etc. Sugar solution, turpentine, sodium chloride, tartaric acid, quartz, quinine sulfate solution, cinnabar, etc. are the examples of optically active substances. So this figure shows the optical activity phenomena. Here, this is the ordinary light representation. This diagram shows the representation of ordinary light which vibrates in all directions. It is also called unpolarized light. When unpolarized light is passed through polarizer, so it converts unpolarized light into plane polarized light. That means plane polarized light having vibrations in only one direction or only one plane. When this plane polarized light is passed through optically active substances, in the emergent light, the plane of vibration is rotates through certain angle. The phenomenon of rotation of the plane of vibration or polarization when plane polarized light is passed through certain optically active substances is called optical activity. So the rotation of the plane of vibration or polarization can be analyzed using the analyzer. So this is the animation picture of the rotation of the plane of vibration or polarization when plane polarized light is passed through optically active substance. This is a light wave having vibration in this plane only. So when this plane polarized light is passed through optically active substance or crystal, the plane of vibration goes on slightly rotating. So the emergent light having vibration in this direction only. So the incident light having vibration in this direction, whereas the emergent light having vibration in this direction. The phenomenon or the property of rotation of the plane of vibration or plane of polarization when plane polarized light is passed through a certain substance, optically active substances, is called optical activity. Types of optically active substances. There are two types of optically active substance. One is dextrorotatory or right-handed. The another one is levorotatory or left-handed. What are dextrorotatory substances? The substances which rotate the plane of polarization in clockwise direction with respect to observer looking towards the light source are called dextrorotatory substances. The substances which rotate the plane of polarization or plane of vibration in a clockwise direction with respect to observer looking towards the light source are called dextrorotatory substances. The examples of dextrorotatory substances are quartz, cane sugar solution, etc. So this diagram shows the dextrorotatory substance, how the dextrorotatory substance rotates the plane of vibration in the clockwise direction or towards the right by looking against the direction of the propagation of the light. Again, this is the ordinary light source. Emit ordinary or unpolarized light having vibrations in all directions is passed through certain polarizer. This polarizer converts unpolarized light into a plane polarized light which is having vibrations in only one plane or in only one direction. When this plane polarized light is passed through certain dextrorotatory optically active substance, so the emergent light contains vibration which is rotating in the clockwise direction, that is towards the right of the observer, which is looking against the direction of the propagation of the light. So the emergent light having vibrations which is rotating in the clockwise direction. The plane of polarization has been rotated towards the right or towards clockwise direction. So the substances which rotate the plane of vibration or plane of polarization. The plane of polarization is always perpendicular to the plane of vibration towards the right or in the clockwise direction for an observer which is looking against the direction of the propagation of the light are called dextrorotatory or right-handed substances. The second one is levorotatory or left-handed substances. The substances which rotate the plane of polarization in an anti-clockwise direction with respect to observer looking towards the light source are called levorotatory substances. Example, fruit sugar solution, nicotine, turpentine, fructose, etc. This diagram shows how the plane polarized light is rotating the anti-clockwise direction or towards the left of the observer by looking against the light source. Again, this is the ordinary light source which produces ordinary or unpolarized light having vibrations in all directions, is passed through certain polarizing filter which converts unpolarized light into plane polarized light having vibrations in this direction. This is called plane of vibration, and the plane of polarization is perpendicular to the plane of vibration. When this plane polarized light is passed through certain optically active solution, that means levorotatory solution like fruit sugar solution or nicotine or turpentine, this levorotatory substance rotates this plane of vibration in the anti-clockwise direction or towards the left of the observer by looking against the source. So these substances are called levorotatory substance. Fresnel's explanation of optical rotation. It is based on the principle that a single harmonic motion along a straight line is the resultant of two circular motions of the same frequency and of the amplitude propagate in opposite direction. So Fresnel's explanation of optical rotation is based on the principle that a single harmonic motion along a straight line is the resultant of two circular motions of the same frequency and of the amplitude propagate in opposite direction. One is in clockwise direction or towards right, and the another one is in anti-clockwise direction. They rotate with the same frequency in opposite direction, which are having half of the amplitude of the one wave. According to Fresnel's, when a plane polarized light enters a crystal of calcite, which is optically inactive substance. Calcite is a optically inactive substance. So it does not rotate the plane of vibration or polarization not towards left or right, along the optic axis only. That means light which is passing along the optic axis only. It is resolved into two circularly polarized vibration rotating in opposite direction with same angular frequency. This is very important. Rotate in opposite direction, both circular polarized light in clockwise or anti-clockwise. They are called opposite direction with same angular frequency or velocity, such that resultant of these two vibrations at all point of time is along the optic axis only. Vibrations rotating in clockwise direction are represented by OR, whereas vibration rotating in anti-clockwise direction are represented by OL. I will show the diagram in the next slide. The resultant of OR and OL at all points of time will be along AB. Vibrations rotating in clockwise direction are represented by OR, whereas vibrations rotating in anti-clockwise direction are represented by OL. The resultant of OR and OL at all points of time will be along AB. So this is the calcite crystal. This is the optic axis. The vibrations which are rotating in the clockwise direction are represented by OR. The vibrations which are rotating in anti-clockwise direction are represented by OL. The resultant at all points, at all instant of time is along OA, which is along optic axis only for a calcite crystal. In case of quartz, which is optically active, so calcite is optically inactive, whereas quartz is optically active. A linearly polarized light on entering the crystal is resolved into two circularly polarized vibrations rotating in opposite direction with different angular velocity or frequency. In calcite crystal, they rotate with the same frequency and angular velocity. But in the case of quartz, the two circularly polarized vibrations rotating in opposite direction with different angular velocity or frequency, depending upon the whether it is maybe clockwise or anti-clockwise. But quartz is always produces clockwise vibrations. In case of right-handed optically active quartz crystal, clockwise vibrations travels faster. Here, this is the calcite crystal. This is the quartz crystal. In case of quartz crystal, the left-handed rotations are represented by OL dash or OL, whereas right-handed rotations are represented by OR dash. At any instant of time, the new position of resultant of OL and OR will be along OC. The resultant of OL and OR dash may be along OC. That is, plane of vibration of light has been rotated through an angle delta by 2 towards right after passing through quartz crystal. Because in the quartz crystal, it is a right-handed quartz crystal. So the right-handed vibrations travels faster than the left-handed vibration. During the time, the left-handed complete one rotation, the right-handed complete one rotation and also advances by an angle delta by 2 or theta. Not delta by 2, sorry, it is rotated by an angle theta because it is travels faster than the left-handed. During the time, the left-handed vibration complete one rotation, the right-handed vibration completes one rotation and also advances by an angle represented by theta in this direction. But the resultant is along OC makes an angle delta by 2. The resultant of left-handed and the right-handed is along OC makes an angle delta by 2. The angle delta by 2 depends upon thickness of the crystal. If the thickness of the crystal is large, then the angle of rotation is large. Angle of rotation. If mu L and mu R be the refractive indices of quartz crystal for right-handed and left-handed vibrations respectively, then optical path difference on passing through quartz crystal slab of thickness T is given as path difference is given by delta is equal to mu L minus mu R into T, where mu L minus mu R is the difference in refractive indices and T is the thickness of the quartz crystal. If lambda be the wavelength of light used, then phase difference phi is equal to 2 pi by lambda into path difference. We already know that phase difference is equal to 2 pi by lambda into path difference. The path difference is given by mu L minus mu R into T. So phi is equal to 2 pi by lambda into mu L minus mu R into T. So angle of rotation is given by this angle phi. The angle of rotation, rotation of the resultant is given by theta is equal to phi by 2, that is equal to pi by lambda into mu L minus mu R into 2, because 2 and 2 get cancelled. So 2 pi by lambda becomes pi by lambda into mu L minus mu R into T. Faraday's effect. So that is the effect of the magnetic field on the rotation of the plane of vibration or polarization of the plane polarized light. Michael Faraday in 1845 discovered that optically inactive substances acquire the ability of rotating the plane of polarization of light when they are subjected to a magnetic field parallel to a propagation direction. This effect is called Faraday's effect. In 1845, Michael Faraday discovered that optically inactive substance, not active substance, optically inactive substances acquire the ability of rotating the plane of polarization of light. That means they become optically active when they are subjected to a magnetic field parallel to the direction of the propagation. This is the direction of the propagation. Parallel to the direction of the propagation, we are applying the magnetic field. This effect is called Faraday's effect. That means again this is the plane polarized light having vibrations in this plane. So for this plane polarized light, and also this is the material, and also we are applying the magnetic field for a material parallel to the direction of the propagation of the plane polarized light. There is a small rotation in the plane of vibration with respect to the direction of the incident light. So that means this is the optically inactive substance becomes optically active, which rotates the plane of vibration towards left or right when it is subjected to a magnetic field which is applied parallel to the direction of the magnetic field. This effect is called Faraday's effect. Once again, this is the direction of the plane of vibration in the plane polarized light when it is passed through optically inactive substance, and on applying the magnetic field B parallel to the direction of the propagation of the light, there is a slight rotation in the plane of vibration or polarization with respect to the direction of the incident light. So incident vibration. So this phenomenon is called Faraday's effect. Optically inactive substance acquire the property of optically activity. The Faraday effect causes a rotation of the plane of polarization which is linearly proportional to the component of the magnetic field, strength of the magnetic field in the direction of the propagation. So the rotation theta is directly proportional to the strength of the magnetic field or intensity of the magnetizing fields. The magnitude of the angle of rotation is directly proportional to strength of the magnetic field H. It is also directly proportional to length of the path of the light in the material L. That is, here L or D represents the length of the path of the light in the material. And the third point is that nature of the transmitting substance. So the magnitude of angle of rotation depends on strength of the magnetic field, directly proportional to the strength of the magnetic field H, length of the path of the light in the material L, and nature of the transmitting substance. So theta is proportional to H and theta is proportional to L. That is, theta is proportional to LH, or theta is equal to VLH, where V is the Wadditt's constant, which is a property of this. Wadditt's constant is the property of the transmitting substance, temperature of the substance, and the frequency of light. This is about the Faraday's effect. Next one is Kerr effect. So, effect of electric field on the plane polarized light. John Kerr discovered in 1875 that optically anisotropy induced in an isotropic liquid under the influence of an electric field is known as the Kerr effect. Optical anisotropy induced in an isotropic liquid under the influence of an electric field is known as the Kerr effect. What is optically anisotropy? Optical anisotropy is the property of material which allows it to change or assume different propagation in different directions as opposite to isotropy. It is the phenomenon of inducement of double refraction of light in a transparent substance when a strong electric field is applied in a direction transverse to the beam of light. Optically, the substance behaves like a crystal with its optic axis parallel to the electric field. So, Kerr effect is the phenomenon of inducement of double refraction of light. That means a single refracted ray is splits up into two refracted ray. One ray is called ordinary ray and the other is called extraordinary ray. That is called inducement of double refraction of light in a transparent substance like glass. When a strong electric field is applied in a direction transverse to the beam of light, optically the substance behaves like a crystal with its optic axis parallel to the electric field is called Kerr effect. So this experiment shows the Kerr effect and it is also called Kerr shell. So this is unpolarized light having vibrations in all directions is passed through certain polarizer which converts unpolarized light into plane polarized light having vibrations in only one direction. So in a Kerr shell, we are applying the strong electric field by placing the two electrodes, positive anode and negative cathode, along the direction of the propagation, and the emergent light is observed through analyzer and it is connected to a detector. This plane polarized light is resolved into two components. Plane polarized light is resolved along two directions because there is an inducement of the double refraction. Double refraction means there are two rays. So one ray having vibration along y direction and the another ray having vibrations along x direction, but the resultant is along z direction. So x component, y component, the resultant of x and y component is along z direction. So depending upon the path difference or phase difference induced in these two components, a light is converted into circularly polarized light. So phase difference results in a circularly polarized light. So this plane polarized light is converted into circularly polarized light when it is passed through a certain cell called Kerr cell. This effect is called Kerr effect. When the electric field is applied, the molecules of the liquid tend to align along the field direction. As the molecules are asymmetric, the alignment causes anisotropy and the liquid becomes double refracting. The induced birefringence is proportional to the square of the applied electric field and the wavelength of the incident light. The induced birefringence is proportional to the square of the applied electric field, that is E square, and to the wavelength, that is directly proportional to lambda. So the induced birefringence delta mu is proportional to lambda and E square, and delta mu is equal to k lambda E square, because induced birefringence is proportional to square of the electric field and directly proportional to lambda. Delta mu is proportional to k lambda E square, or delta mu is proportional to lambda E square, or delta mu is equal to k lambda E square, where k is a constant called Kerr constant. So these are the books I have used for a reference. Thank you for watching.